Hello, this is lecture 2 on the course variational methods in mechanics and design. In the last lecture we discussed what variational methods can do for mechanics and design or structural optimization in particular. When you say design, structural design or structural optimization. Now we look at the main topic, which is calculus of variations, which is the basis for the variational methods. In calculus of variations, there is a long history that we need to discuss. That is what we will do. So, we will talk about the genesis of calculus of variations, or rather how this field, this mathematical field came into existence. So, here is the outline of today's lecture. First, we will discuss how this field evolved, and we will also discuss what problems define this field, because usually interesting problems call for a new mathematical technique, and we will discuss those problems that defined the field of calculus of variations. And then we will mention all the people who did important contributions to calculus of variations. So, we get a sense of history of this field. What do we learn in this lecture? We will done two things. One is we learn about brief history of calculus of variations starting from ancient times to 20th century, and we will also look at importance of calculus of variation in many fields. We will be discussing only in the field of mechanics and structural design or structural optimization, but we will mention what other fields also have applications of calculus of variations, because it is a very general tool. Okay. Let us consider this very old problem, goes back to the time of Pierre de Fermat, who lived in the 17th century, 1607 to 1665, and his problem is put in a rather daily life like thing. Here let us say you are at a swimming pool and there is a dog, and let us say this is your dog there, and then there is a rubber duck that you have thrown into the swimming pool, and you ask your dog to fetch it. Okay. Dog has certain speed of running on the floor of the swimming pool, and duck, in order to fetch the duck, it has to also swim in the swimming pool water. There is a swimming speed, and these speeds are different. Let us assume that dog can run faster on the swimming pool floor as opposed to swimming in the pool. So, which path does a dog take to go from where it is now to where the duck is? Three different paths are shown. The solid line here refers to the shortest distance path, right, because that is the line joining the 2 points, that is the shortest distance. But is that the shortest time path is a question, right, because the dog has to go fastest to the duck. If it takes this straight line path, what happens is that it will be running some distance on the swimming pool floor and some distance in water swimming. So, instead let us say it takes a path that looks like this, that is dog starts from there, goes here and then goes here. This way the distance in the pool, swimming distance, is the least, but it has to run longer distance on the floor, right. So, that may not be the fastest again, even though swimming speed, which is lower, and hence the distance is minimized, but overall distance increases. So, what is the best path? Okay. And there are different curves are shown, and we can draw many more curves, right. So, we can draw a number of curves. One of them is going to be the least time path. Okay. This problem, although it is put in a daily life situation, but actually that is what light rays also do, and that is what was the observation or hypothesis of Pierre de Fermat. That is why it is called a Fermat problem. Fermat has lots of problems after his name, this is one of them. So, light rays, when they go from point A to point B, which path do they take? Let us say here we have air and here we have glass medium. So, A is in air and B is in glass. For it to go, it has certain speed in air and certain speed in glass. So, which path does it take? Same problem as what we discussed here with a dog and a rubber duck. Okay. So, here light ray, Fermat conjectured that it takes the least time path and not least distance path. Okay, that is the difference. least distance path is a straight line, we know it, but what is the least time path? Okay. Let us pose this as an optimization problem. So, let us say that point A and point B are separated by the distance L horizontally and distance H vertically, and let us say that it will hit the glass and air interface at this point, okay, because we said that going from here till here and then going that way, that is from A all the way here and then going this way, is not going to be the fastest path because overall distance has increased, and definitely this is not the fastest path because if we go back to the swimming pool analogy, if the swimming speed is less here compared to air, then this will not be also, right. Somewhere in between let us make that variable h, that is what we do not know. Once we know that h, this point gets located, then we know A to, let us say this intermediate point C and then C to B, and that will be very clear. So, we have to know this h. How do you find that h? Okay. In order to find h, we can pose it as an optimization problem to minimize the time taken from A to C plus time taken to go from C to B. The total time will minimize with respect to h and we get the answer. Okay. So, let us pose it as a finite variable optimization problem. So, there is distance S A that the light ray would travel from A to this point which we called C, and then C to B distance is S G. So, if you look at that, first let us assume that in air it has a speed of V A and in glass it has a speed of V G. Okay. Then the time of going for this point from A to B will be time to go from A to C, which is that S A distance divided by the speed which is V A, and then from C to B is this term S G divided by V G. And what is S A? You simply use Pythagoras theorem, where we have this L A square plus h, the total h minus small h square, that is S A, and then S G is L G square plus h square, okay, because how much is L A, how much is L G is also known to us. So, we know how to get S A and S G, but they do depend on this h. So, in order to minimize that time t, which will be S A divided by V A, S A we have here divided by V A, S G divided by V G, we have this total expression. Our variable is h, which is indicated in red, that is what we are minimizing with respect to, and all these are known quantities data. Okay. So, we have a function of h which we have to minimize with respect to h in order to find the least distance path, which is segmented path A to C and then C to B. So, minimize this. In order to minimize, the condition is that the slope, or rather the first derivative dt by dh should be equal to 0. That is a condition for a minimum and a maximum, but now we are taking that is a minimization problem. In either case, the first derivative should be equal to 0. So, you have to take derivative of t where the expression is known, differentiate this with respect to h, which is done here for this first term and the second term, which is shown here, and we simplify a little bit and move terms around. So, we get an equation like this, h minus h divided by V A times square root of L A square plus h minus h square, that is equal to h divided by V G square root of L G square plus h square. Okay. We still do not, if you want we can solve for h here, our aim is to find h, we can solve for it. We have an equation in h now, which we got by equating derivative of t with respect to h equal to 0. We have the equation, we can solve for h, but instead let us look at what is in here, which is this is the condition that we got in the last slide, that is dt by dh equal to 0 gave us this equation. Now, we recognize that this part, okay, the one that I am circling now, that is nothing but sin theta a, okay, where sin theta a, if I indicate that this is the angle. So, sin theta a would be with the normal, let us say this is theta A, okay. That would be that h minus h, which is this one divided by this quantity that we have, this hypotenuse which we have now. Okay. So, if you look at that, that is sin theta A, and this will be theta g, okay, sin theta g. This other one, this part is sin theta g. Okay. Now, what we have is what we call Snell's rule of refraction. Sometimes people call it a law, and that is not correct, because we say something is a law which can, if it can only be verified by experiment, but here it is not true. We have derived it by following Fermat's conjecture that says light rays follow the least time path. So, light ray follows the Snell's rule. If you say, the rule itself follows from optimization. Okay. So, in this problem we have derived what is normally called Snell's rule of refraction by assuming that light rays take the least time path. Okay. Now, if you look at this problem, we originally said that there can be lot of different curves, right. So, we have a number of curves, we wanted to get the best curve that minimizes the time, but we have used it as a one variable problem and defined this h, which is from here to here, okay, not from here to here, from here to here, and made it a one variable optimization problem, got a solution and recognized that as Snell's rule. But later on, much later in this course, we will revisit this problem to interpret it as if it is a continuous curve, how that leads to this non-differentiable point, or what we call non-smooth path. So, the very first problem in calculus of variations has a non-smooth curve as a solution. This is a curve, only thing is it is two straight lines that are piecewise continuous. At this point there is a non-differentiable point, that is derivative is not uniquely defined at that point, there is a kink in the path, and that can be handled in the framework of calculus of variations, where we say there is an unknown function. If I call this y of x, that unknown function itself can be computed. If while talking about light rays, let us also talk about reflection. Let us say we have a point A and point B, and there is a wall here, and we need to go from A to B, but in between we must touch the wall once. Okay. That is, again there are several paths. I can go like this, right, or I can go like this, and several other ways, right. I can, if I want, I can go here and then go this way and so forth. There are several paths. Which one do you take? Which path do you take? The same question as what we asked in the case of refraction, we can talk about that in the case of reflection also. If you actually work out this problem, you will find that the light rays, even in the case of reflection, they try to find the optimum time path. Okay. Optimum time, I do not say optimal again, optimum time path. You can try this problem by assuming again, let us say this distance, where it hits. If I call that some x, okay, then it will go from here to there, because this distance is A and B are given with respect to the wall. So, if we say this is x, we can solve the problem and get the answer. Okay. But this is true with diffraction also, not just reflection and refraction, but also with diffraction. Okay. If you work out the problem, minimize time, in this case of reflection, time and distance are the same, because you are in the same medium where the speed is the same, right. And optical theory of diffraction or geometric theory of diffraction also uses this optimum time path to get solutions, okay, because light rays try to minimize their time. They are always in a hurry, even though they are the fastest things that move, but they try to minimize the time to go from one place to other place. Okay. It actually fits with the nature of light rays, right, because they are the one that can go as fast as or faster than anything else. Okay. All right. Okay. But then Notice that I am saying now optimum time rather than saying minimum time. Okay. The reason is that when you say optimum time, it can be minimum time or maximum time, right. It can be a minimum or a maximum locally, right. In the vicinity of those, it can be minimum or a maximum. Sometimes let us say we take this example of a circular mirror, right. There are 2 points A and B. Now we say the same thing, I want to go from A to B, but I have to touch the mirror wall, okay. Basically it is about reflection to go from there to here. There are several paths, right. I can go from here, touch the mirror here and go there, or go like that and go this way, or go like this and come back to B. There are several paths. Of all of these, which one will you take? It turns out if you solve this problem, that is you take let us say in order to locate a point, you take this as angle theta and then minimize the time taken with respect to theta. At theta varies, that is where the light will fall there and then come here, right. So, if you vary that angle theta and get the time to go from here to here to here, then you minimize it, you will find that not only minimum exists, there is also maximum. So, light rays actually take optimum time path. So, that was the correction made to Fermat's conjecture. They do not take the least time path always, they take the optimum time path. Sometimes it is maximum, sometimes it is minimum. That is something to bear in mind in this problem. Okay. So, historically this is one of the problems where you have a non-smooth solution, but it is a calculus of variations problem. Newton, who lived after Fermat, he had a problem of his own that fits the calculus of variations. He wanted to find the optimum shape, what is shown here, this shape, okay, which is surface of revolution, which is for a body that is moving in a fluid, what shape will minimize the drag on it, minimize the resistance of fluid on it as it is moving in the direction that is shown here. When it is moving like this, what particular shape will have the least drag. Okay. But this problem has not become very popular in the history of calculus of variations, because Newton apparently had made some mistakes or some assumptions which were not valid later on, but he had thought of this. Many other people might have thought of problems like this, where the unknown is a function. That is what we had discussed last time. The unknown itself is a function. Okay. So, this problem is a classic problem in calculus of variations, which is again points A and B. So, go to from A and B different conditions. Here under the influence of gravity, different curves are shown. There is a straight line joining A and B, and the blue curve and red curve, and the black curve or a green curve. We have all these curves, and let us say a bead is starting there, and then due to gravity it falls down, right, in various ways, right. Among all these curves, which one will make this bead fall from A to B, separated vertically by distance h, separated horizontally by distance L, again the least time. Okay. Which path among these? If you say straight line like an inclined plane, that is a least distance path, but that is not least time path. Okay. This is the classical problem that started calculus of variations historically. Okay. So, here we have to note some historical details. One is that this problem was posed by Johann Bernoulli. There are 4 different Bernoullis, this is one of them. In 1696 he posed this problem in a mathematics journal and gave time till Christmas for everybody to respond with answers, and at that time he had solved it himself, and he also had a brother named Bernoulli, Jacob Bernoulli, he also had solved it, and Leibniz, who was his close associate, he had also solved it, and L'Hopital, whose name you must be familiar in the case of limits, finding limits. These including himself, Jacob Bernoulli, Leibniz and L'Hopital, 4 people had solved, and then he was actually waiting, Johann Bernoulli was waiting for the solution of Newton, but Newton had not responded. So, he sent that problem again to him without writing a personal letter, because they were rivals in mathematics and mechanics and other things. So, Newton saw that, he got a little irritated, apparently he reached home at 2 o'clock in the night, and his niece gave him this problem and he solved it and only went to bed, and then he sent it to Johann Bernoulli, the solution, without even signing the name, right. Then Johann Bernoulli saw that solution, it was obviously correct. Another solution, this is a fifth solution to the problem, and he immediately recognized that as Newton's because of the elegance of the solution that Newton had sent. So, the famous quote that Johann Bernoulli made, even though Newton was his rival, is to say that the strike of a lion can be told by looking at its paw, the imprint of the paw on that. So, that means that Newton's stamp was there in that solution. Anyway, 5 people solving a problem gave birth to the field of calculus of variations, okay, where the unknown curve, in this case the straight line and a kinked straight line is not a solution, a continuous curve is a solution. That is why this problem has become a classical problem in calculus of variations, and that goes by this name, if you can read it. Okay. That is basically Greek, which says brachistochrone, that in English is brachistochrone problem. Chrone means time, brachisto is the root for least or minimum time problem. So, Fermat problem also was minimum time problem, this is a minimum time problem. This is more famous because the solution of this is a continuous curve. People try to determine what that curve is. All these 5 people that we talked about in the previous slide had actually solved it. This problem where point A to B, the speed changes continuously, unlike in the refraction problem. Refraction problem, there are only 2 speeds in air and glass, or swimming pool floor or in the pool itself, right. Whereas here it is a falling body, their acceleration only in the vertical direction and nothing in the horizontal direction, right. It is only guided by this wire or a path. So, here the speed of the bead at different points is continually changing. So, you have to derive an expression for it and pose the problem, unlike the refraction problem that we looked at. Okay. There it looks like this. So, when you actually get the time, it is an integral now. You take a small piece here and call it ds, and then say how much will be the fall here, and because there will be some speed and you can get the speed of that at that moment, and then see how much distance you get the time, you will get a small time to go from this point to this point, and then integrate it from 0 to L. If you take your axis here like this is x and this is y, then y of x is our function. In terms of y of x, it turns out to be this integral 0 to L square root of 1 plus dy by dx square divided by v of y, which we have to derive from conservation of energy. So, loss of potential energy of the mass equal to kinetic energy gained by the mass, based on that you can get the speed. So, mg h minus y, let us say it is at this point, that will be the y here, okay, that is y. H minus y is the height through which the bead has fallen, that is from here to here, right, that will be that h minus y. Mg, that is potential energy lost, is kinetic energy gained, we can get the speed v. Okay. So, we get the speed v at that point. Now, the problem becomes where the v was there, we substitute this square root of 2g into h minus y. So, this one basically comes because the small dx ds that we take there, that using Pythagoras theorem, this is dx and then dy, that is ds will be square root of dx square plus dy square, that is our ds, okay, that is our ds, okay, and that ds is put here. Now, what we have done is we have taken dx out, okay, of this, that becomes 1 plus dy by dx square dx, that is why we get this. So, this integral later we will know what this is called, it is called a functional, okay, it is not a function, it is a functional. Okay. If you minimize this with respect to y of x, In the refraction problem we had only one variable called h. Now we have a function y of x itself as an unknown, that is the nature of calculus evaluation problem. This is the classical brachistochrone problem. Okay. And it depends, as you can see, depends on the function y of x and its derivative dy by dx. Now, if we want, we can actually solve the light refraction problem, brachistochrone problem in a similar way, right. If you think of this discretization here, as the speed increases, let us say we take this interval very small, thinking that in that small time, short time, this path is very small. So, we can assume that the speed is constant there. We can get the speed, changing speed there, and so forth. We can actually pose it as a what we did light refraction problem and sum it up, right. So, if you do all that minimization with respect to all these different heights, you can solve it using finite variable optimization problem, and that is how Euler ended up solving, as we will discuss later. But anyway, the solution for this problem that we posed, which is to minimize that integral with respect to y of x, the solution is a well known curve, well known at that time also, called cycloid. So, cycloid is a special curve which as we can see the animation, when you have a disk rolling, a point on the disk will trace a path, which is what we are seeing here. A point on the disk, as it is rolling, it traces this red curve, that is a cycloid. If you take part of that, if this is our point A, okay, and this is point, this curve is the cycloid. Okay. So, the cycloid, we have here the other cycloid which is vertically flipped, and there is this green line which is line joining points A and B. Now, if all these 3 points, that is this, okay, so we have this point and this point and this point, all 3 points, let us say, start at the same time at A, and there is gravity here. So, let me get the pen. Let us say there is gravity this way for point A to point B, then B, the beat that followed the cycloid curve is already there, already close to point B, whereas these two are lagging behind, right. In this particular instance, these two are at the same horizontal distance, need not be, this takes different time, this takes different time, but the question is that cycloid, or answer is that cycloid gives you the least time path from A to B. Okay. So, that is the brachistochrone problem for which solution is a cycloid. A century before that, Galileo also had thought of problems of this kind. All of you might have heard that Galileo was doing a lot of experiments with inclined planes, because he realized that gravity is trying to pull the things down, and he knew that there is a force. He was trying to figure out what is the effect of the force. So, he was trying to do this, drop masses from Leaning Tower of Pisa and other things and inclined planes. He realized that if he has one inclined plane, such as this one from A to B, when it reaches B, it will reach with certain speed, which you can verify if it goes horizontally how far it goes, right. Instead, he realized that if he puts 2 inclined planes like that, it takes less time, that is what his experiment showed. And then he realized that if he takes 3 inclined planes, okay, there is a segment here, a segment here, right, then it takes even less time. Then he thought, how about a circular arc? If you put a circular arc from A to B, that also reduce the time. So, he basically he saw the circular arc as a limit of all these several segmented multi inclined planes. Okay. Then he started asking the question, A to B, if we have points A and B, between A and B infinite number of circular arcs can be drawn, among which one of them is going to have the least time for the ball to reach from A to B following that path. That is a problem he posed. Some people say that Galileo was mistaken, because he thought circular arc is the brachistochrone curve, that is the curve that minimizes the time, but actually it is not true. If you read Galileo's book Two New Sciences, where he actually probes which circular arc among all possible circular arcs that pass through 2 points he gives the solution as one particular circular arc. He was not thinking about any other curve, okay, which is what Bernoulli later realized. You can see when Galileo was, right, he was in the 16th century, almost a century before Newton, and in fact he lived before Fermat also, okay, or at least they were contemporaries for some time. Much earlier, now we are going back to the ancient world, Hero of Alexandria, who lived in BC 1500 BC to 300 AD. People are uncertain exactly when he lived, right. He had thought of this light rays problem. So, it was not something that Fermat was the first one to think about. He also had thought about what light rays do. Do they take the least distance path or least time path, but then he was not able to do experiments or conclude one way or the other. But other people who thought about calculus variation type of problem, one of them is called the isoperimetric problem. Okay. Let us say that you are given a piece of string. Okay, let us say I will take, yeah. So, let us say that I am given a piece of string like that, okay, and I need to arrange that into a closed loop such as the one that is shown here. The length of this from here to here, let us say the L is given to you. Now, we need to arrange it in a closed loop fashion, so that the area enclosed by it is the largest. Okay. The smallest is easy, basically you can take this and loop it around this. So, it will be, if they are very close, you get 0 area, right. Now, you have to enclose such a way that it encloses the maximum area. So, that is called Pappus of Alexandria problem, or isoperimetric problem, or Queen Dido problem. There are different stories, but the same thing. Every ancient culture there may be a story around this type of problem, where you are given a certain rope or a string of certain length, and you need to put it to a particular shape to enclose the maximum area. Okay. We will consider mathematical shaping of this problem later on, actually next lecture. But this is also calculus variation problem, where you have to find this function that defines the shape of this closed curve, so that it gives you the maximum enclosed area.